Hi, my name is Gregory Preston. Today I'll be presenting alongside my partner, Kolin. We will be presenting the Turkey Student Data Evaluation data set. This data set was comprised of several different variables. Of utmost importance were about 28 questions that students were to respond to, and based upon these responses we would in turn attempt to predict the difficulty of the course that they were enrolled in prior to them completing it. This was our business purpose. Specifically, it read, to predict the course difficulty based on exit survey responses received by students from a Turkish university after they've completed their respective course. Let's take a look at the data set. The data set that was used was comprised of 5,820 records. These were all student survey responses. Within that data set, 28 of the variables were distinct questions that were categorical in nature. They ranged from 1 to 5, with 1 being strongly disagree, 2 being disagree, 3 being neutral, 4 being agree, and 5 being strongly agree. Within the data set, there were other variables that existed, such as the instructor, the course code, the number of repeats for a student who might have taken the course more than once. However, based upon our particular scenario and what we chose as an output, we decided to go ahead and eliminate those variables. In the end, we retained the difficulty of the course as the output variable and the 28 questionnaire question response variables as well. The good part about our pre-processing phase is that the data came to us very clean. It was almost as if it had been pre-cleansed. There weren't any outliers, there weren't any missing data. We ran several histograms and charts just to look through the data to see what we would be working with, and we found even distributions across the board. We didn't find any variable that was not selected or any option that had not been selected by any of the students. So we were able to take that and really focus in on the algorithms and what types of results that they would produce. As an example down here, we have a chart of the difficulty variable, which was our output variable. Again, it ranged from 1 to 5. As you can see from this frequency distribution, Category 1 accounted for 27.84% of the occurrences, and Category 5 for 11.2% of the occurrences. The smallest category was Category 2 with 9.43% of the total occurrences on the difficulty variable. So all in all, we decided to keep this the way that it was. We didn't want to group anything. We wanted to leave it exactly the way that it was and give ourselves some type of a challenge. And of course, we'll be getting to the challenge a little bit later on in this presentation. Here we have a very nice chart. It includes everything from the difficulty through the Q1 and Q20 through Q28 variables that we used in our initial run. Now this is prior to the pre-processing phase being complete. You'll notice once again, this is just to reiterate, there's a very nice distribution of each one of these components. There isn't a single category that you would see that hadn't been used, hence there were no outliers. Okay, fun stuff. Here's the challenge. We were presented with one issue. There were 28 questions amongst the data set, as well as the difficulty variable, producing 29 variables, resulting in 29 variables. Far too many. What we needed to do, we need to come up with a model that would be a little more parsimonious, a little bit cleaner to paint the big picture of what's going on in the data. So we had 3 options. The first option was the PCA analysis, which we decided to forego. The second option was to create a classification tree, and using that model we determined which variables that the algorithm saw as being significant. The third option was to use a linear regression model, much the same way as we had the classification tree where it identified its own significant variables. We felt that the linear regression would do a good job as well in doing that. What was interesting is that running both models produced very different outputs. As you can see, the regression model identified Q1, Q8, Q16, and Q17 as being significant, and this of course is based on the p-value. The linear regression, on the other hand, identified 5 variables as being significant. That's Q5, Q14, Q17, Q18, and Q22. Just to backtrack on the regression model, the p-value really was an output. That was determined based upon the tree that was drawn, the full tree, that is. And my partner Yuri will talk about that shortly. So the end result was that we had these 8 coefficients, and there were 8 because Q17 appeared in both of the models. The 8 coefficients would be used as inputs, and we keep this going forward throughout each of the models for each one of the runs that we had. So we ended up with Q1, Q5, Q8, Q14, Q16, Q17, Q18, and Q22. I now turn it over to my partner.
Hello, my name is Yuri. The first algorithm that we used on our dataset was classification tree. It was created based on partition worksheet using a cutoff value of 0.5 with 5 levels of display and a minimum of 349 records in each terminal node. Based on the data returned from the confusion matrix, the best pruned tree could not identify a general accuracy rate due to possibly multiple levels of difficulty exceeding 2. Because the level of difficulty exceeding 2, the error rate was very high. We can see right here it was set at 64.26% in a 4th node decision node. Based on the high error rate and the fact that our chart could be explained using only 4 significant variables, we decided to rerun this model, and for the second time only using questions 1, question 8, question 16, question 17 as inputs, and leave the level of difficulties as of output. On the next slide, we can see the output for our second run. Our second run was based of 4 significant variables, as I mentioned before in a previous slide, and the results of the second run had an identical outcome with the first run. By comparing the confusion matrices, the error rate did not change at all, and it was set at the same error rate of 64.26%. In both scenarios, the most influential variable was question 17, which we presented in the next slideshow with the decision tree chart. The tree attained from the second run had 4 levels with 9 nodes, which was identical to the full tree from the first run. On the classification confusion matrix, it created predicted and actual classes for this model. It shows counts of cases that we correctly and incorrectly classified. For our example, let's take column 1, which was assigned to the level 1 of difficulty with a total number of 1075 cases, and out of total the model correctly identified only 395 cases correctly, and the rest, it was split between the rest of the levels between 2, 3, 4, and 5. Same scenario we can see on the level 3 within the model, where out of 1,253 cases, the model identified only 264 correctly. With these results, since model confusion matrix didn't generate a accuracy nor targeted traits, we decided to run manual models, and they created accuracy rate of 35.74%, and the targeted rate was identified as a 24.92%. On the next slide, we have a full tree for since 2 models were basically identical in their outcome, they represent both models. The most influential variable was question 17, which can be found at the root node. It had 4 levels, 1, 2, 3, and 4, and 9 nodes. Not 9 nodes. And the output was our level of difficulties, and our model identified only 2, level 3 and level 1. By going to the next slide, we can see our if-then clause based on this model, and converting the tree to the simplified if-then clause would read as follows. If question 17 higher than 3.5, then difficulty level would fall in level 3 of difficulty. Else, if question 17 less or equal 3.5, then difficulty level would fall in a level of 1. It should be noted that although the second and third levels of the tree refer to question 1, question 18, and 16, it is the root node, which is question 17, that determines the outcome of the terminal node at the initial split. This observation allows for the simplified if-then clause to maintain accuracy, although a more detailed if-then could be used. And as example, if question 17 less or equal 3.5 and question 1, in this case it doesn't matter if question 1 will be less or equal 0.1 or higher than 1.5, it still falls in a level 1. Next model we ran, it was linear regression, and Gregory will cover that part.
So, with the classification now done, we move on to our second model, which is the linear regression model. As indicated earlier, we were committed at this point to using the 8 variables that the combination of the classification tree and the linear regression model deemed significant. So here we go again. These are our input variables, with the difficulty being the output. We ran this through an exhaustive search, and what we tried to do is figure out what the best subset would be. There were a lot of valuable information in this run, this initial run for the linear regression. Here, using those same 8 variables that we saw earlier, you'll notice that this model, of the 8, it found 4 to be significant. These would be considered significant because they were less than 0.05 as a p-value. Now, overall as a model, our R-squared was extremely, we don't want to say low, because again, we're just reporting the data, but it was, in my opinion, lower than anticipated, with 0.0229 as a R-squared, or 2.3%. We expected better results. Going back up, if we needed to look at the logit, or the difficulty as it would equate into a formula, we could take this constant term, which is 2.395 plus 0.0006 times Q1 plus 8 times Q5, and we go straight down this list, and that would represent our logit. And like I said, there was a wealth of good information here. Looking at the subsets, ideally we'd like to choose one of these subsets, but again, with the adjusted R squared column so low, we really weren't 100% sure how to proceed. So what we chose to do is to do a second run using these 4 variables only that the model deemed significant. Let's skip through the first run for a bit. I'd like to show you guys one thing that we, my partner and I, realized when trying to create the predictive variable or use the predictive value that was created from the chart or from the algorithm. What we did first, we got a count on the number of variables, or rather the number of records that were in this run. So we came up with 3,492. From this point, we then took the number of instances of each one of the variables just to get a total count. So we can sort this by these areas here, 1, 2, 3, 4, and 5 individually, and this will give us our total counts. Now we're looking at the training set right now, which is the way that you want to do it. From that point, whatever you have as your predicted, we sorted it from highest to lowest, and in doing that, we had an idea based on our counts of which values would represent our cutoffs. So as an example here, our total count for, let's start from the bottom, from the highest number, which is 5, because this is sorted highest to lowest. So our total count for 5s is 372 in the training run. So what you do, you highlight starting with the first value here, so you get to 372. Going down. Okay, and right here we see that our first cutoff value is actually 2.995,70342, which I've indicated here. From this point, you would then count down 739 for your next grouping, and so on and so forth until you get to the very bottom. Just to be on the safe side, I'm going to see what the sum on this is, 3,492, which is exactly what we got in our actual value count. These cutoff values basically mean that that predicted value belongs to that group. So if we were to look between, say, 2.828 and 2.995, those would be all of our expected 4s. So based on these cutoff values, we then apply that to our validation training set, or validation score, sorry. So I've just plugged those same values up here, and now I'm manually just looking at the actual cutoff value. So anything that would be 2.995 or greater would be considered a category 5. Anything between 2.82 and that 2.995 would be considered a category 4. So these are our counts. This, once again, this is the validation set. So we use the training score to find the cutoffs, and we apply that against the validation set. Back to the PowerPoint. So these are some of the things that we found, and this is for 2 separate runs. Again, the very first run was a run where we took the 8 distinct variables or significant variables based on the combination of both the classification tree and the linear regression. So on the left here, our first run, which is the linear regression, for the 8 variables, it barely outperformed naive Bayes. So just by circumstance, it's probably that 3% or 2%. I don't recall what the R-square was, but it was very minimal. It barely outperformed naive Bayes. The same thing happened when we did the 4 variable run, which is the second run. Very identical lift charts, not much doing there. The decile wise, again, this is very comparable. Both charts look nearly identical, with the left chart just ever so slightly, actually the right chart maybe even ever so slightly nudging out the left. But once again, the performance was not as great as what we'd expect. So going back to what we identified in the validation set as our category 1, 2, 3, 4, and 5, we had our counts, and this is the confusion matrix that we manually had to create. You may recall that the linear regression does not create its own confusion matrix, so we had to do it the hard way. Over here, you see that the number of strongly disagrees that were predicted and the number of actual strong disagrees was 265. For the agrees, which would be a number 2, predicteds match up with the actuals 29 times. And you follow that downward pattern from 265 to the 29, 337, 116, and the 36. And that would represent your general accuracy when you take that sum and you divide it by the total, which is 2,711. And you come out with the general accuracy rate for this first run of 28.88%. Again, this is the first run. When you take into account the number of times that the predicted matched up with the actual on an individual level, meaning strongly agree, where we see our 265, you want to divide that by that total on that same line, which would be the 772. 265 divided by the 772 gives you the 34.33%, and you'd proceed down each one of these categories in that manner. Taking the average of these values, we came out with an average targeted accuracy rate of 23.95%. I hope that's clear. It took us quite a while to get the hang of it.
Neural network. The final analysis technique employed the use of the neural network classification algorithm. Due to multiple levels of difficulty, we ran this model several times to get a better idea of how and what the algorithm was generated as a result. The first run was done using the following variables as input: question 1, question 5, question 8, 14, 16, 17, 18, and 22. The difficulty the difficulty variable was again selected as the output. It was created using a cutoff value of 0.5, one hidden layer with 25 nodes, and the number of epochs was set to 30 as a training option for defining the neural network weights and possibly to minimize error values. Next slide contains the first outcome of a neural network model. The results were generated based on the validation data consisting of 2,328 trackers. The confusion matrix shown in this slide created 5 categories for both the predicted and accuracy rate classes. The error rates were very high still, and at some levels it even reached 100%, like in this case level 5. Comparing this model run to the classification tree, there was a slightly higher error rate with this model. The classification tree produced an overall error rate of 64.26%, and the neural network produced 65.42%, resulting in a difference of 1.16% of a difference. With such a high error rate, we decided to increase number of epochs for the second run, and the output is shown on the next slide. The number of epochs was increased from 30 to 60. One weakness of the neural network is that it can easily overfit the data with an increased number of epochs, which can cause the error rate on validation data set to be too large. With the number of algorithmic options being increased from 30 to 60, the error rate slightly decreased by 0.26% and was 65.16 on the second run. Same tendency shown in a comparison of general accuracy rate between 30 and 60 epochs. We can see that the second run generated a slightly higher rate of 34.84% in comparison with the previous model of 34.58%. One interesting observation when running the second model with increased epochs numbers from 30 to 60, second time it was expected that to have a higher rate of error. However, in our case, that error rate decreased. For the comparison of a confusion matrix, let's say between neural network and classification tree. Classification tree Yeah, in our case, classification tree identified only 2 levels out of 5 for the confusion matrix, and those levels were level 1 and level 3. However, for neural network, this model could identify all 5 levels of difficulty, and it generated slightly better output. However, it's still let's take for comparison level 1 in the first column. Out of total of 332 cases, this model could identify only 177, and the rest was mistakenly identified. And basically, same output were done for the rest of the levels in our model. As a conclusion for our analysis, what we can say that with such poor performance among each of the models, it was determined that there was not true correlation between 28 questions and level of difficulties whatsoever. And a comparison of each confusion matrix had mixed results with a number of unexpected events. And with the neural network, for example, it appeared that difficulty levels 1 and 3 were predicted more frequently, while with the classification tree, difficulty levels 1 and 3 were predicted exclusively. Within the linear regression model, difficulty level 2 and 4 were predicted mostly inaccurate, and level 1 and 5 had no predictions.
And just to expand on what my partner Yuri mentioned in the conclusion, there really wasn't much of a correlation with the exception of question 17 amongst each one of the models. So what we chose to do, we chose to take a look at question 17 just to see what it was. And it turns out that question 17 was actually related to whether or not the instructor came to class on time. So we found that to be pretty interesting, although we know that we just report on it as if it were question 17 and nothing more. The other thing, just to touch on the linear regression, I know in the presentation we did not include the second run. The second run that included the 4 variables also performed very poor. As a matter of fact, it was lower than the 8 variable run in that it had a lower R value, and also according to the variables themselves, they just didn't perform well at all. So this was an excellent learning experience, and if anything, the takeaway is that you don't always get a model that's going to tell the perfect story. It's not always going to work out the way that you expect. Sometimes there really is no correlation. Thank you.